Right, again, we're talking about rotational kinematics. We could talk about a solid body that's rigid. We start with rigid solid bodies partly because that's what we often do. A non-rigid solid body would be if my shoulder rotates and my arm doesn't, or everything's disconnected, so it's pretty hard to relate the different pieces. So a rigid body would be like that. Or an object traveling along a circular path. So either way. And again, the good news is it's kinematics. It's the same idea, except we have to be careful. We did revolutions to angles, angles to revolutions. Now we need to do angles to tangential components, tangential motion versus tangential motion to angles. Again, when you get used to it, it's really quite nice. In fact, they're related, angles to tangential, by, we're going to see the radius R, or sometimes capital R, and we'll talk about that distinction. So let's see how that works. When we talk about displacements, angular, what do we use? Because you're on video. Delta theta in what units?
Radians.
Radians, and I'll show you why. Okay, delta theta in radians. So I often put a subscript down there just to have you remember that. Because, and watch out for your calculators. Sometimes you put it in radians, and then you want to gaze, and you mess up. We've all done it. So catching once or twice. So that's all that is. The angle in radians. Why do we need it in radians? I'll show you. Tangential. So tangential is an arc length. Sometimes people use S, and not usually delta S, but you could. So, or some people will use L along the path, and you'll see this in math classes as well. So whatever it is. And I kind of like S or delta S in what units? Meters, right? Centimeters, nanometers, inches, feet, whatever. So meters, say for now, just to keep it not too overwhelming, but you can convert units. Cool. So what's the connection? Well, the connection, again, we go back over here. We go back over to this little piece of pie, or pizza pie, if you will. And the interesting thing is here, we're not doing revs to radians, right? We're going to do radians to a length. So how do we find this? This is key. It's just this simple. If I take a full circle, I can slice it into 360 little degree slices. Small little wedges. So now your pizza isn't a bunch of appetizers. Or you can slice it into radians. How many radians in one circle? 2 pi radians, which is about 2 times 3 or 6 radians, right? Or 6 1/4 if you want. 6 1/4, about radians. Make sure you can do rough calculations as well as looking at precision. So how big is a radian? What is a radian? It's simply this. This guy, and say this. Well, if I look at this, if I go let's talk about the tangential. And go relate it to the angular. So let's do this for once around, because you know this. Once around. Sorry for my scribbles. So tangential, once around, how far do we go? What do we call it once around? We call it the circumference. We could call it C, which is also S once around. And again, we can't say that's equal to an angle because they're not the same, but they are related to an angle. And once around, the angle, delta theta once, times the radius, which is to say, of course, the radius times 2 pi radians, or, as we frequently write it, and no one cares, right, 2 pi r. And so you see that, in fact, the definition and where pi comes from, pizza pi or dairy pi, is this. Any arc length is equal to the radius and this is worthy of doing at least once here, times the angle in what? In radians. It's only true because if the circumference around, take a string, measure the circumference of any circle, right? Measure the circumference, divide, take that string and measure the diameter, which is this. That's the diameter, isn't it? Take the circumference, divide by the diameter, and you should get something close to 3. Close to pi. How well how close you get to pi depends on your measurement technique, right? So that is, the circumference divided by the diameter is a little more than 3. Pi radians is half a circle, that's 180 degrees. 180 is a big difference between 3. 2 pi is about 6, not 360. And so this is only true, and that's where radians, how radians are defined. We can say this, delta theta in radians is equal to the arc length divided by the radius. Now what if the arc length equals the radius? So if S is equal to R, imagine that picture. Here's the radius, so let me make that here. Can you get that in there, Rudy?
Yeah.
That's about, let's do it right there. There's my radius, R. And then I'm going to try to go along a circle that same distance, but something like that. I'll do it in purple. Here's my S. Critical idea that's going to come up in all of this, not hard, just overwhelming because of a lot of stuff, is that we aren't moving along the radius. Right? It's not a very good circle, is it? Now, if S equals R, we tried to make it about the same, we have a certain angle here of what? Then delta theta radians equals S over R equals 1, doesn't it? And 1 what? 1 radian. People often call radians a dimensionless unit because it's meters divided by meters, centimeters divided by centimeters, inch divided by inch. Right? But I like to keep the radians in when you're doing this analysis, certainly while you're learning. Keep the radians because there's a difference. And so what I often call, and now that we have the video, I can take the time, too much. This is R in meters radial. Now, no one does this, but You'll see as we go in with torque and things like that. It's a little interesting. A Newton meter is a joule, and a Newton meter is not a joule. A Newton meter is torque. A Newton meter is a joule. Don't worry about it now. We'll come back to it. So there's meters that you move and meters that you don't move. It's tricky. You could totally get it, though. Totally get it. It's just overwhelming. Everybody cool? It's critical. You have to get this. There's no way. There's no way to move forward without it. So that's the definition of a radian. Anyone know? Let's see. Let me go over here and finish this relationship up. What's the relationship between radians and degrees? We use degrees a lot. Well, obviously 360 degrees is physically equivalent. They're both angles. So once around is 2 pi radians, which is to say, you can use it this way. And so the conversion factor, or the relationship, would be 180 degrees over pi radians is physically 1, physical unity. Or you can pi radians per 180 degrees, and you can certainly convert between those two. So it's that easy. Okay, cool. So you get to rewind, and you do this. The best way to do it is look at it like usual, get a little acquaintance, then use it. Then look at it, then use it. And you will, it will open up huge doors. So when we talk about this, the relationship is the R factor, and we know that if I want to write it this way, I can have that S is equal to some radius, meters tangential is equal to meters radial times radians, or radians, this is a really critical thing, is equal to meters tangential divided by meters radial, or whatever units you want to use for length. So that's critical. Okay, so once we do that, we can do everything else. So I've got rate of travel, omega. We can do average or instant. And we can do rate of travel here for S is going to be have an instant or average, delta theta, delta t, whichever one you're using. Then we got velocity tangential. So that means tangential, but we often just write it with a t. Is by definition ds dt, meters per second. Boom. How do I get between them? The same way I get between theta and s. That's why we did all that. It's the R factor. So that means that Vt is equal to R omega. Or omega is equal to Vt over R. And again, we can use average, delta theta over delta t, or an instant like this. And I want to now remind you that we can write this in derivative form or integral form. So we can go between this as delta theta is equal to the integral omega dt. If omega is constant, just pull it out. But otherwise, put in that function earlier to later. And let me remind you that, of course, this is the old school stuff, is that S or delta S, I just write that because people so often do, is V tangential dt. Derivative form, integral form, again, common. And then when we go to acceleration, we've done this last one. Acceleration is by definition d omega dt, which can be written in integral form as delta omega is integral alpha dt, earlier to later. Same old thing. Same old thing. Just writing it in symbols of angular or radian. So to here, a tangential, this is going to be a key thing, is by definition dv tangential dt, the rate of change of speed. And remember that a radially in is equal to the speed squared over the radius, which gives you, if you look at the units, meter per second squared, which sometimes we will write, let me see, V tangentials are omega, r squared divided by r, omega squared. So I can think of that as r omega squared. And now you almost have your rotational kinematics, and you just work with that for any problem. So let's just do one more quick one, and then we'll get on with feeling rotational inertia. So.